All right, y'all ready? It's 3 o'clock. So, let me change that. I'm gonna put it on the new line. Give me 1 second. Once it lets me, I'll put it on a new line. And then that's just your general operation. So let me add those 2 lines there because I can figure out how to do it and pull everywhere. But hopefully that daily table now makes a little bit more sense when you see it like it happens. So based on that daily table, does this form a group? Maybe also 303. Oh, it's kind of important to have. That's nice. Was clear. What happened then? Okay, see if you can bring some more pull there. I guess you get the benefit out of all of us. But all right, let's do. Oh, I need to unmute so we can hear Shanika. Shanika, can you give me a mic check, please?
1 2 1 2.
All right, thank you. All right, so everyone got answers in? I haven't checked. That's why I was asking. All right, only got 3. So I'll say you got about 30 seconds left for that 303. Well, 303. All 5 of you in? Yeah, I've got all 5. So just in case you want to change answers, I'll give you like 5 seconds, technically. All right, 3, 2, 1. Let the answers happen. So, why does it not form a group? Because it does not form a group.
No identity.
Yeah, we've got no identity element. And remember, if you don't even have an identity element, there's no way you can talk about inverses. Inverses depend on there being an identity element. And a quick way to see if there is an identity element is I look along the way I order my elements in the very first row. So these are all elements in my set. I'm trying to make a group with. Do I see that same exact repetition X, Y, Z anywhere in any of those rows? Nope. So I know there is no element that I can operate on the left-hand side of X, Y, or Z that will just generate that X, Y, or Z. I can even do a similar thing for the column. I've got no column here. That I do get 1 column, so X, when I multiply on the right-hand side, right? It does act similar to an identity, but it's only on the right-hand side. It doesn't work on the left. So no group here because no identity elements. Any questions though? So. All right, so I said today, we're gonna prove left and right cancellation properties still occur in groups. Because remember, what are other than a binary operation, i.e. it's closed, what are the other three things, the only other three things we have to work with inside groups? You know, the operation is, it's binary operation, but it's also, it's associative. So if we're working in a group, the only things we're guaranteed is the binary operation that's associative. We have an identity element, and every element has an inverse. That is all you're guaranteed. So we technically, until we prove it today, are not able to say, hopefully it's up. That if I take A and operate on the left side of B, and it's equal to A operated on the left side of C, then B and C have to be the same thing. Our axioms, what makes up a group, does not directly guarantee that. That's something that we still have to deduce. And similarly, if I leave it on the right side, so B operated with A and C operated with A, if those are the same, then B and C have to be the same. And why do we have to check both directions, both sides of the operation? We're not guaranteed it's commutative. Groups are not commutative by nature. They potentially can be. They're not always. So let's do our first. It's going to be similar either direction. We're going to write up both. So which one do you want to do first? You want to do left cancellation or you want to do right cancellation? Do left. So we're going to let G be a group. We're going to choose three elements. We're going to call A, B, and C. First up, we're going to let A times B equal to A times C. And just knowing the fact that I have associativity, that I have an identity element, and that every element has an inverse, I can show that B is going to be equal to C. Well, if I'm in a group and I kind of want to get rid of A on that left-hand side, what would I probably want to multiply that A by to get rid of it? So if we were thinking back to kind of real numbers and multiplication, it would be 1 over A. But that is a concept of what in groups? Yes. The inverse. So you want to multiply on the left or operate on the left by the inverse. That's what's going to get rid of that A there. But hey, because I'm in a group and A is in that group, I'm guaranteed what? There's an inverse. Once G is a group, there exists the inverse of A in G such that A times A inverse is equal to A inverse times A, which is equal to my identity element, which we always reserve to be represented by E in general, unless you know what it is. So now I know because A inverse exists, I consider that starting equation. A times B is equal to A times C. And now, what am I going to do to each of that equation on this side?
Sorry, is that an E?
Yes.
Oh, okay.
That's me trying to fix it.
Oh, okay.
Probably made it worse for you. No, don't ever hesitate to ask for clarity. Is that better?
Yeah.
So A times B is equal to A times C. What do we want to do to both sides of that equation? Operate it with A on what side of each expression? On the left hand side. Multiply both sides of the equation on the left by the inverse of A. So that when I look at A inverse times A, what do I have? Not one,
E.
my identity element E.
If you put it on the right, like it would be A, B, A inverse, that's incorrect.
Well, what can I do with that?
Because can't you like move around, A?
That requires what property?
What,
You're able to rearrange the order that requires us to be commutative. Are groups commutative by nature? Don't get missing that. That's what makes things difficult. Because we're so used to always being able to assume commutativity, now we're gonna say, nah, you don't get that anymore. That's why multiplying on the left is very particular, and multiplying on the right is very particular. Good question. So going back to my proof, then it's E times B, the identity element times B is equal to the identity element times C, but identity elements, that special element. E times B is just gonna result in what?
B.
B, and E times C is just gonna result in C. So we now show left cancellation. And it's all dependent upon the existence of inverses and an identity. How much do you think the argument's going to change when I go to the other direction, right cancellation? Not much. Let BA equals CA. This G is a group. There exists A inverse in G. That A inverse is equal to A inverse A. It's equal to my identity elements. We can consider B times A is equal to C times A. Now what am I going to do? I'm testing you because I want to make sure you're using the language.
What's on the right?
Yeah, I'll play on the right by the inverse of A. So then I'll be left with B times A inverse equal to C times A inverse. If I take any element, multiply it by its inverse, it becomes D. Identity. I take the identity element, multiply it by anything else, change. So I get then that B is equal to C, and again, all because inverses exist. That is what guarantees that left and right hand cancellation. And now that we've proven it to be true inside of groups, guess what we can now start to use? Yeah, community. Left hand cancellation, right hand cancellation. We can now start to employ them. All right, what questions you got? Thank you. Hey, I got two people speaking. All right, let's go on to more products. We're gonna let G be a group. Let A be some element of that G. And what we're gonna show is that the inverse for whatever that element A is has to be unique. So every single element in a group has a unique inverse. How do we prove something is unique?
Saying somebody else is the same thing.
Yeah, so say there's a second object that acts just the same way. Show it must actually be the same object. Assume that there's two, show that they have to be the same. So proof. Let G be a group. And let A be an element of G. Then we know there exists an inverse element in G. So set A inverse is equal to A inverse A. It's equal to my identity element E. Essentially just clearly stating there is an inverse element and the properties of that inverse. Now what am I going to assume? I've given you one inverse. What's the next thing I should assume for uniqueness?
Another inverse.
There's another inverse. So assume that there exists, it's going to say A star in my group, such that A times A star would be the same thing as A star times A, which is equal to my identity element. Using all of this information, my goal is to show that A star and A inverse, or A to the negative one, are the same element. Well, because A star and A inverse are acting as inverses of the element A, I know that A times A to the negative one is going to be equal to what element?
Oh,
E, my identity element, right? But how can I use the identity element to then create an A star in this string of equations, or bring up an A star in this string of equations?
equal it to A.
Equal to A times A star. And I have to be careful with that choice. That you chose the right one, or the correct one. Because then I have overall, this implies A times A inverse is equal to A times A star. And now what can I use to easily say,
Wait,
well, I can technically apply inverses, but I don't even need to go through that process.
like A.
Divide by A. What was it that we just showed? What was the property of groups that folds that we just showed before this theorem?
Multiply by the inverse.
Y'all are getting there. Left cancellation, right cancellation. If A times B is equal to A times C, so as long as I'm multiplying on the left by the same elements, these two are equal. I know that B and C have to be the same. What do I have here in this group? A times A to the negative one is equal to A times A star.
So A inverse and A star have to be the same.
A and A inverse and A star have to be the same by what? Yeah. So we assume there was a second one. Should have had to be the same as the initial one that we started with. Therefore, inverses are unique. So within groups, we still get left-hand calculation because of inverses. And I could technically make that same argument. I know A inverse is an inverse of A, so I can multiply by A inverse on both sides. I have A inverse times A, which is identity element, then you become A inverse. Now I have A inverse times A, which become an identity element. I have identity element times A star. Which then become A star, right? That was all the work that we already did in theorem. But I have to reinvent the wheel. Just say, hey, we've already proved that this is true. Because of this, let's use it. Trying to say what you were suggesting before by multiplying by inverse is wrong. Just more work. All right, what questions you got for me on this? No, don't go away. Just on a new page.
You saying that because we do the left hand, we don't have to do the right hand?
No, we proved right hand as well. I'm just saying, since we've already proved left-hand cancellation, I don't have to go through every time I want to apply that concept. I don't have to go through the same steps that I used in proof. I can go ahead and use its correct result. Next property that we're going to show the groups. To use my phone, sorry y'all. If we consider the inverse from two elements being operated together, actually the inverse of the second element operated with the inverse of the first element. We get to prove why. And if you go back, this is the same, if you somehow remember this from linear algebra, it's the same property that you can matrix inverses with multiplication. You take A from the matrix A times the matrix B and then invert it. It's the same thing as B inverse times A inverse. Part of the reason why. All right, if I'm going to prove this, what do I get to assume? Well, A and B wouldn't have identity elements. Identity elements are property of the group, right? You could say they have inverses, which is just innate in being a group. So the only things we get from just the statement of theorem is that we get a group, we get two elements from our group. Let G be a group. And let A and B be elements of that group. But because we know that this is a group, then we know there exists an A inverse and B inverse a group such that A times A inverse A is equal to my identity element, and B inverse is equal to B inverse B is equal to my identity element. All right. That's really all I have to work with, right? Technically, I have left-hand cancellation, I have inverses are unique. Now I have my operations associative. So that's it. So we know by definition, AB will result in something. So that when I multiply it by the inverse of that product, it should be equal to what elements? My identity elements. And I should be able to look at AB inverse times AB. And that should also result in the identity element. Here I'm using green just to kind of represent that the scratch work process is involved, right? This is our goal. What should I do?
You should equal the equation for other, no, equal it.
We'll end up doing that, yeah. Right? Show something about the inverse of A times B, and show something about B inverse times A inverse to hopefully get that it's equal. Right? Well, really quickly, we technically get one more thing that I forgot to make sure we put in there. Since we're in a group, if I consider A operated with B or A times B, that's still an element of the group. Yeah, binary operation, right? Takes any two elements from the group, creates a new element of the group. So A times B is in the group. Well, if it's in the group, does it mean it also has an inverse? So since A times B will be an element of G, we know there exists an inverse element to this such that AB times AB inverse equals my identity element, and I guess I can write it the same way now you have been doing it. AB inverse and AB is also got to be equal to my identity element. So yeah, I was right. If I can just end up where I have AB inverse, that A times B, all of it to the -1, have that in an equation where I see a B inverse A inverse up here as well, maybe some left hand or right hand cancellations, I can then show that they're the same. So what are we going to do?
Multiply.
We're going to have to end up multiplying some things together. Question is just what, right? Well, let's take this and multiply it by what I'm trying to show the inverse is of A times B, another way to represent it, which is B inverse times A inverse. So I take my element AB, I multiply it by B inverse times A inverse. But hey, what's happening in the middle there? B times its inverse. And because this operation is associative, I can choose what order I operate these elements. Right? I'm not switching where they're at on either side of the operation, but I can choose which ones to do first. Then B times its inverse is just going to create what? The identity elements. So then wait a second, whether or not I do A times the identity element or the identity element times A inverse, what am I going to be left? Yeah. So technically, just to take it step by step, first apply the identity property, multiply by anything that doesn't change, and then I'm left with A times its inverse, which is B. But wait a second. What else do we know that's going to be useful for what we're trying to show equals the identity?
B times inverse.
Says B times A inverse.
Wait, no. Is it like B times A inverse times B?
So no, I mean, B times A times A inverse times B inverse would result, but it wouldn't help us prove the result that we're looking for. What's the result that we're looking for? That inverse element of A times B is really just the inverse element of B times the inverse element of A. I know that I can take A times B and multiply it on the right by its inverse element, AB all to -1. And what does that result in? E, my identity element. What also resulted in my identity element? A times B times the inverse times A. So what can I conclude? Well, then I know A times B inverse times A inverse has got to be equal to A times B times the inverse of A. Wait a second. What can I again apply now to get to the result that I'm wanting to show? Left cancellation. In both of these expressions, I'm multiplying on the left-hand side by A, and then by B. Then I'll be left with what I'm looking for, right? So take it step by step. I can get rid of A by left-hand cancellation. This will be the same thing as B times B inverse times A inverse is equal to T times A B inverse. And then get rid of the B, leaving me with B inverse times A inverse is equal to A B inverse by applying left cancellation a second time. Is that what I was trying to show? Okay. So am I done? Therefore, the inverse is the same thing as the inverse times the inverse. And all I needed, other than the axioms for being a group, left-hand cancellation. Isn't it weird how powerful that simple concept is? You're also welcome to say no to that. I think it's powerful. You're welcome to say that. And just a side note, I guess if you wanted to correctly argue that AB regarding an element in my group is just represented by multiplication of two different elements, you can still just apply left-hand cancellation once to AB and so result. So that's what your brain thought first. You're not wrong at all. I was just being very meticulous with my group. All right, what questions you got? All right. Not a theorem yet, but another thing that we can employ in groups, just kind of hijacking that term of multiplication, is exponents. Because exponents, if I just think about it back in algebra terms, that's just indicating what? Yeah, repeated multiplication of the same element, right? If I x cubed is x times x times x. So we can do the same thing for talking about group elements. I can operate an element of a group itself multiple times. So we can use exponent notation. to represent repeated operations. We often refer to abstractly as multiplications. Again, even though we're saying multiplications, we're not referring back to multiplication of the number of real numbers or integers or something like that. Just a blanket term. So that means a to the nth power is a times a times a times a, where I do this 10 times. Then what do you think a to the 0th power is going to be? Oh, 1 is a real number. Are we working with real numbers? No, but it's not a bad thing. That's what we tell you, right? Any real number to the 0th power is always 1, but that's because with multiplication, 1 is acting as what particular element? It's the identity element. So why does that have to change? Because anything to the 0th power in a group is going to be equal to the identity element for that group. What happens if our exponent is negative? You know. Well, you'd probably say, okay, if I gave you, make a little room. Later, if I said 2 to the negative 4, how to rewrite that so I don't have a negative exponent? Yeah, 1 over 2 to the 4, 1 divided by 2 to the 4, which is really just 1/2, or the inverse of 2 multiplied together how many times? 4 times. Would it make sense to change up that generalization, or if we can generalize it, would it make sense to change that up at all? No, right? Because real numbers with multiplication excluding 0 is still a group. Real numbers with addition is still a group. Where did I put the pen? Oh yeah, here. Then when we consider a to a negative number, what we're really saying is take the inverse of a and operate it with itself, the absolute value of 10 times. Just like what we were saying here, 2 to the negative 4. Well, the inverse of 2 under multiplication is 1/2. So I take 1/2 and raise it to the 4th power. And just to make sure you see it, so a to the negative 3 means we're taking what and multiplying it by itself how many times? Just be a inverse times a inverse times a inverse. All right. What happens if I have exponents? The exponents, bases are the same. Exponents are different. Add the exponents together because I have n multiplications of a here and n multiplications of a here. So when I add them all together, there's a total of n plus n multiplication. So our normal exponent properties still hold. So far. What if I do an exponent to an exponent? Multiply them together, and that still holds because I'm just doing n multiplications of m multiplications of a. Giving me a total of a to the m times n. What about a times b n power? Well, if you're working in the real numbers, you tell me distribute the n to both terms, right? Do you want to say this is a to the n times b to the n? But wait a second. That is relying on a property that we don't have. Because just by how it's defined, I'm saying take a times b and multiply it by itself n times. So what is that string of multiplications going to look like?
AB times AB times B.
AB, AB, AB. N times, I'll add in parentheses to make it a little bit easier to see. Well, if I wanted to get a to the n out of it, I'd have to be able to rearrange the order of these multiplications. So I can move all of my a's to the front and all of my b's to the back. That means I'd have to have what property? I want to rearrange the order of my operations. Commutativity. We have commutativity in a group. Yeah. So I can't rearrange. That's only true. It's only going to be true that you can kind of do this distributed property if you're working in an abelian group. If you're in an abelian group, then you do have what property? Commutativity. Then I can reorder the order of those multiplications. We have to be very critical. Very, very critical of what we're working with. There's a lot of what we assume to hold true might not.
You have to assume that we can't do that unless you specifically tell us that it's an abelian group.
Yep. Or if your statement is specifically involving it and dealing whatever statement you're in. Let's do one proof before we get out of here. Kind of deals with this. Let G be a group. And let A and B be elements of the group G. Then AB quantity squared is going to be the same thing as A squared times B squared, if and only if AB is equal to BA. Which essentially, if this is holding true for any general elements A and B, I'm really saying this group is what type of commutative group or abelian group, whichever term you want to use. So essentially we're going to prove what? But as a couple of you forgot in the homework, the if and only if proof, really this breaks down into how many proofs? Two of them, right? I get a forward implication and a reverse implication. Forward implication would be just based on the order that I wrote it. I get to assume A times B quantity squared is the same thing as A squared times B squared. I want to show that AB is equal to BA, and then vice versa. I would assume commutativity and then show A times B squared is equal to A squared times B squared. So let G be a group. And let A and B be elements of G. Which direction do you want to do first, forward or backwards? Forward. So we're gonna let AB quantity squared be the same thing as A squared times B squared. So now I have to use this, and just based on time, I'm not going to take as much of a Socratic approach to it as I usually like to. So what I'm going to do is I'm going to consider A times B squared. I know two things about it. One, that this is the same thing as AB times AB. And based on my assumption, my hypothesis, I know it's also equal to A squared times B squared. Because the transitive property of equality still holds the groups. Hopefully an obvious assumption, but I'm not reminding everyone. Then this means A times B times A times B is the same thing as A squared times B squared.
But that's not commutative.
Not commutative. A times B times A times B is the same thing as A times B squared. And then now A times B squared is equal to A squared B squared. I get AB is equal to A squared times B squared.
That's not rearranging it though.
That's not rearranging at all. Where did I reorder the elements?
Because you went from AB to AA. That's rearranging. You could.
AB to AA.
Okay,
Where?
now man, again,
Okay, yeah.
again.
No, keep asking questions. I want you to understand what's going on. So
I see.
perfect. But now I can imply two things: left cancellation and right cancellation. By left cancellation, I can get rid of that a's. By right cancellation, I can get rid of those b's on the right hand side. And what am I left?
BA.
BA is equal to AB, but same thing as AB is equal to BA. Is that the result that I was trying to show for the forward implication?
Yeah.
This. If I assume that it's kind of up here, A times B quantity squared is equal to A squared times B squared, then I know AB has got to be equal to BA. We could do the reverse implication very quickly. Because you're essentially saying, I assume that these two things commute. So if I look at A times B quantity squared, that's just by definition AB times AB. But what can I do with that B and the A that's in the middle of that nice little string of multiplications? What can I do with this A times this B here? Based on my assumption from the hypothesis, B times A is the same thing as A times B. So I can rewrite that B times A that's in the center here as That's it. P times B. I'll highlight it just to make sure that's obvious. Which then gives me, I have A squared times B squared. And I've done both implications, both directions, finally proved, argue, nice little solid square. So it's past 3:50, and I know it's hot, so I'm not gonna make y'all stay in here any longer. If you have questions though, feel free to stick around and ask. Otherwise, I'll see you on Wednesday. All of your homework twos are graded, solutions are also posted as well. I think the biggest mistake that anyone made was just forgetting to do both directions for the if and only if statement. And that was only some of you, not all of you. So don't forget